Thank you for joining me today. We will continue the mechanical properties of material. Previously, we covered that if we have steel sample under tension, we can construct the relationship, the typical relationship between strain and stress. And we found that the typical relationship looks like we have linear relationship, and the slope of this linear relationship will give you something called modulus of elasticity or Young's modulus. Then we have yielding plateau. Then we have strain hardening until we reach to the ultimate stress. Then the necking stage will start until we reach to the fracture of the sample. Sometimes this plateau does not exist. The yielding behavior of the material is not clear enough to figure out this is the value of the yielding stress or sigma yield, whatever the symbol. So by the end of the linear relationship, we should have this plateau, and this plateau is very clear that we have yielding. But sometimes we don't have this clear indication of yielding. The curve, after we finish up the linear relationship, we are going to start with the strain hardening directly. In this case, how to figure out the yielding stress, we have a method for this case, which is called offset method. So, in most metals, however, constant yielding will not occur beyond the elastic range. So after the elastic range, after the linear relationship, we don't have clear plateau, clear constant yielding. So this metal often does not have a well-defined yield point, and consequently, it is standard practice to define yield strengths using a graphical procedure called offset method. What is the meaning of offset method? In this method, we are going to figure out a value of strain equal 0.2% or 0.002. After you measure this value of strain, I will draw a line parallel to the linear relationship at the beginning of this curve until you hit the curve at a point. At this point, we can say this is the value of the yielding stress. So we are going to use 0.2% strain is chosen, and from this point on the axis, a line parallel to the initial straight line portion of the stress strain diagram. The point where this line intersects the curve will define the yielding strength or the yielding stress. So if we have a relationship which is not typical, if we have a relationship between strain and stress for some of the metals, and this relationship, we have a linear relationship, then a curve without a clear definition for the yielding behavior, in this case, I'm gonna measure here a value of strain equal 0.2% or 0.002. That makes sense? This is the value of the strain, 0.002. Then I will draw a parallel line. Parallel line to what? To the linear relationship here. So this line is parallel. Extend this line until you hit the curve. At this intersection, go ahead and measure the value of the stress. This value of stress will be the yielding stress. That makes sense? Otherwise, we will have a clear definition. Plateau, this constant value of stress, This constant value is the value of the yielding stress. If we don't have this case, we are going to have this case. So we can figure out the yielding stress by offset method. We have an example here. In this example, we have a tension test was performed on a steel specimen having an original diameter of 12.5 millimeters. So we have steel rebar specimen with initial diameter here D equal 12.5 millimeter, and the gauge length of this specimen equal 50 millimeter. This specimen will be tested under tension, and we have these data recorded during the test. What is the applied load and what is the corresponding elongation? We need to draw the stress strain diagram. So first of all, keep in your mind, I will convert the value of the load to stress. This stress will be the applied of the load or the force divided by the cross-section area. In this case, your cross-section area will be pi divided 4 times diameter square. This area equal to pi divided 4 times diameter square equal 122.7 millimeter square. Keep in your mind, I'm going to convert the elongation value to strain. This strain equal the elongation value in millimeter divided by the original length of the specimen. This original length equal 50 millimeter. Once you converted the recorded data to strain and stress, I can start to draw the typical relationship between the two values. So we have this Excel sheet with the recorded data, load, and elongation. So I will stop here and write, I'm looking for the value of the stress, and I will make it in megapascal. That makes sense? So I will stand here equal this value of the load. I will multiply it times 1000 to be in Newton and divide it by the value of the cross-section area, which is 122.7. 122.7. And then I will go back to this cell and double click on this little part or this little point. So this calculation will be repeated for the whole cells. In this column, I will start to figure out the value of the strain. Equal this elongation divided by the original length of the specimen. The original length was 50 millimeters, so divided by 50. And then I will repeat this calculation to the rest of the cells. Once you find out the value of the stress and the strain, I will start to draw. Insert X and Y scatter curve, smooth curve. Then right click on this chart, select the data, add, and what is the X value? So click on this button. The X value will be the strain. So I will select all of these cells. Enter. What is the Y value? Just click this button and select the values in this columns. Then enter and okay. Okay. Here is the stress strain curve, stress strain relationship. Unfortunately, we don't have a clear indication of the yielding stress. So what should I do? Make it bigger. There you go. We don't have the typical stress strain curve, which looks like this. Linear, plateau, then strain hardening, and the end of the curve. this indication of the yielding. We don't have this one. So how can I figure out the yielding stress? Because one of the requirements after you draw the stress strain diagram, we need to figure out the yield stress. In this case, we are going to use the offset method. So I need to measure a distance here equal 0.002. So this one is 0.05. This one will be 0.025. So 0.002 something here. Does that make sense? So I can probably, we can make it more clear if we can change the scale of the horizontal axis to be the maximum is not 0.3. We can make it the maximum is 0.05. Let's try this one. Maybe we can make it 0.02. There you go. Yes. In this case, I can take copy from this one and make it smaller. There you go. So I zoomed in. I zoomed in because this value is 0.05, so I need to locate 0.002. So it's very hard. So I just zoomed in. So 0.005, that means this value at the mid will be 0.0025. So 0.02 looks like something here. Here you go. At this point. So this value will be 0.002. Excuse me. Or 0.2%. After you locate this point, I will go ahead and draw a parallel line. This line is parallel to this line. That makes sense? At this intersection, approximately, we will have the yielding point. So the yielding point looks like something around 350. So this is the value of sigma yield. Does that make sense? So this method is called offset method, will be used if we don't have a clear indication or clear constant stress that will give you the value of the yielding stress. In this case, I will draw a horizontal value of strain equal 0.2%. From this point, I will draw a parallel line to the linear relationship. The intersection with the curve will give you the value of the yielding stress. If you would like to figure out the ultimate stress, the ultimate stress is the highest value of the stress. Let's go back. Here you go. The ultimate stress is the highest value of the stress. Looks like we have a value equal 525.6. So the highest value of the stress will be this value, which is 525.6. So sigma ultimate will be 525.6 megapascal. And the value of yielding stress equal 350 megapascal. What else? So we are done with the yielding stress, ultimate, excuse me, ultimate stress, and we have friction stress. Friction stress is the last value of the stress at the failure, which is the last point on the curve, which is 479.2. So fraction stress equal 479.2 megapascal. This is the value of fraction, sigma fraction. This is the value of sigma ultimate. And this is the value of sigma yielding. What is the Young's modulus? Young's modulus means the slope of the linear relationship. What is the slope of this linear relationship? This one. So E, I am going to select one point, just one point, for example, this point, and I will get the slope from this point. So this point, which is this one, the value of the stress is 90.46. So I have 90.46 will be divided by the value of the corresponding strain, 0.0035, will give you the value of the Young's modulus equal to 58457.1 megapascal. Or you can divide it by 1000, it will be 258.4 gigapascal. I just divided this value by 1000, so I converted from megapascal to gigapascal. This is the value of the Young's modulus. We need to figure out the modulus of resilience and modulus of toughness. If you remember, the modulus of resilience is the area under the linear relationship. Looks like this linear relationship ended up at this point, which is 308, and this is the corresponding strain. So this linear relationship looks like this. I will zoom in. So the linear relationship ended up at a value of stress equal 308.1 approximately. 308.1, and the corresponding strain was 0.00204. So the area under this linear relationship will represent the modulus of resilience. Modulus of resilience equal 1/2 times 0.00204 times 308.1. So 0.5 times 0.00204 times 308.1. So the value will be 0.31. This is the modulus of resilience. What is the value of modulus of toughness? If you remember, the modulus of toughness is the area under the curve. So we need to figure out what is the area under this curve. Do you remember how can we figure this out? We covered this in the previous videos. I will divide this curve to strips. At the recorded data, I will divide it to strips. The area of one strip equal this value of stress plus this value of stress divided by 2 times the value of the strain, the increment value of strain. Looks like a trapezoid. And then I will add the area of these strips together to find out the area under the curve, and I can do it using Excel. So I will sit here, not at the first one, but at the second one, and I will say equal. I will open brackets, this stress value plus this stress value, the next one. I'm sorry. Wait. This stress value, the first one, plus this stress value, the second one, divided by 2. So I found out the value of the stress at the edge of the trapezoid and the value of the stress at the end, then time the increment in the strain, this value of strain minus this value of strain. Does that make sense? So this is the area of the trapezoid. One more time. then enter. I can find out the value of the first one. So one more time, we have the curve looks like this. So we have different values recorded here. What I did, at each value, I divided this curve to strips. Each strip looks like a trapezoid. For example, if you would like to figure out the area of this trapezoid, so we have a value of stress here, and we have a value of stress here, and we have increment of strain. So the area of this strip will be sigma 1 plus sigma 2 divided by 2 times the value of the strain increment. I will repeat this for each strip. This is what I did. I did for the first strip, then double click to be repeated in the next strips. Once you find out the area of each strip, I will say equal sum. I will do summation for all of these strips. This value will be the modulus of toughness. So the modulus of toughness will be 117.1. Modulus of toughness will equal 117.1 megapascal. That makes sense? This is how to figure out the different values or different properties of a material with a stress strain curve without a clear indication of the yielding stress.